All right, week 126, building my own operating system. And shout out to anyone in Europe right now. It is hot right now. It's hot these days. Very, very sweaty kind of day, but we're gonna still do it. We're still gonna get out there, do some hobby operating systems development. Yo, Cat Flare. Glad to see you, man. Yeah. Straight up. Yeah, shout out to 37 Celsius for sure. It's like I can't even sit down. I'm literally gonna try to stand up for the entire stream today, if possible. It's just so it's just so hot. Um, let's see, we're building. I literally haven't touched the OS since last weekend, so we're gonna pick directly back off. What's up, hello code? Nice to see you. Euro trip, experience 40C. Budapest, that is wild, actually. That, yeah, that's very hot. Sub Trolley Cat, nice to see you. And we got the gang in the chat. That's awesome. Lane, what is up? Lane 1313, nice to see you, Lane. All right, gang. I'm just gonna get into things as usual. Man, I'm literally like I'm sticking to my desk right now. Yeah. So 126. It's June 28th. Let's talk about what we're gonna do. So last week we finally made some progress. Well, we always make progress, but we finally landed on a pretty good implementation and design for my kernel stacks, guard pages, stuff like this. At least a very initial implementation. Does it run? I kind of forget over page faulting, but I think that was intentional. In our tasks. Yeah, so the last time I left things off, the kernel just boots up and it runs this function which tries to write to the guard page, and we expect it to page fault. So that's working as it should. And then I think if I comment this out, we should keep running our basic test, which what am I doing? Kernel.cpp. I have the OS configured to just run 4 of these tasks, and it should just be doing the normal working thing. So one thing I really want to do at some point is set up some integration tests, because and what I mean by that is it's really annoying that I'm rewriting the kernel tasks that get run on boot to test various specific functionality, and it's super messy. It would be really cool if I had some kind of infrastructure where I could be like, yeah, I want to test writing to a guard page and verify that if I do that, we get a page fault, for example. And that's just like one test that runs. And I don't need to like weirdly comment out this line in and out of the kernel to do that. So I'm just going to, I don't know, submit that to the ether and say it would be cool. Tests, e.g. writing to stack guard pages, page fault, or even just doing the basic scheduling tests. Run some tasks and they yield between each other. Yeah, I'm straight up. Oh my, this is crazy. I'm sticking to my desk. Can I, okay. I'm gonna get a shirt. This is wild. It's so hot. All right. Yes. Subadizia, Luffy. In my dreams. Yeah, so this is how as far as we got. We can even check out, I'll stop the kernel. We can even just check out, so what's in the working tree? Commenting some stuff out and deleting this unused task stack pool. So this was just some stuff we worked on last time, moving some ad hoc code out of the constructor of the task and into a function on the task stack, so that, or a member function on the task stack. So that's kind of cool. That produces some pretty nice looking code. I'm pretty happy with how that looks. That makes our task just look like this. It has a bunch of these things. It gets past a few things, and then in the construction, it just calls .init on the task stack, which sets up the landing pad and returns back the RSP that the stack pointer should be set to on entry into the task. Yeah, trillionaires in the chat. Yeah. Yes, sir. Okay. So what I want to look into today is this sticky. Don't store the task stacks inline in the scheduler. Awful for padding / wastes a lot of memory. This is actually super embarrassing. Let me show you what I mean. This is kind of messy. Let's clean slate, schedule to HPP. So here's what I mean. I have a scheduler struct right now, and it has some members. It's like some kind of normal members. It has some pointers. It has some data. And then it has like, currently it has 32K of buffers. Because it's storing all the, right, the idea is we're doing upfront memory allocation. We're not doing dynamic memory allocation. And so the idea is to just statically allocate the memory for the task stacks, which is what this looks like. Each task stack is currently 8K, which is even small. It's going to be bigger when we actually make the task stack like actually larger. And then we have a number of them. It's currently 4, it should be way more. And so this is, let's just say, yeah, like, yeah, let's say we even, we have 4 tasks right now, 32K. We could get 10 tasks, that's 80K. Get 100 tasks, that's 800 kilobytes straight up in this struct. So that's bad, clearly. What's up, Weezo? So yeah, we want to move this out. We don't want this to live really directly in the scheduler object. That's kind of weird, but what I'm sort of thinking is that, and this is what we sketched out last time, seems like it would be better if there is like some just dedicated area for really large buffers. So I'm just going to start prototyping that. I think it's been so long since I have cleaned up the Git history. A lot of stuff has happened where I'm still on this dev branch, which even adds basic infrastructure like interrupts and stuff. And then for the longest time, we were just doing stacks and stuff. So I will clean this up eventually. I think I will branch off here though and call this kernel buffers, for lack of a better name. I've been working on this for 126 weeks. Damn, that's true. It's mostly true. I mean, there's been a lot of different phases in the 126 weeks, and we're in the newest phase, obviously, but strictly speaking, like, to be really strict, it hasn't been this exact OS the entire time. I was like working on this other OS for about a year and then switching over to this one. So, but yeah, so the idea is to not have this. So what do we want instead? I'm just going to HPP. I'm just going to call it kernel buffers. For lack of a better name, I do not know what the actual name for this is going to be. And the AI is kind of getting in the way again. So kernel buffers, yeah, then that's the question, is sort of like what, okay, so it's gonna have something like scheduler buffers, scheduler buffers, and then we need to scheduler, and then over here, so the idea is to I just want to have a separate object that yeah, so now we have the scheduler buffers, and this is where large buffers will go. And the nice thing is that this then allows the scheduler to not embed the data, it just gets a pointer to it. And then now the scheduler is going to need to store a pointer to the scheduler buffers. Call it and it could even be an internal type. Yeah, there's options. What's up, Abhishek? Weezo asks, why are you making it? Bunch of different reasons. Mostly just because I want to learn about how operating systems work. And also, it's just a lot of fun, actually. I have to say, it's a lot of fun to work in this little project that I've built from scratch, and I understand how it works, and it's using all this nice technology that I really like to use. And it's something I can be proud of, so yeah. So yeah, obviously, yeah, this is not great. These should all be consistent. They should all probably use the braces style. Yeah, I mean, maybe let's talk about doing it this way. Internal struct called buffers. Lane asks, do you have any favorite C++ books or resources? I have a lot of C++ books since I love the language. It's a good question. Let me think. I have some favorite C++ talks, like CPPCon talks. There's this one talk, it's from Facebook. It's like the 10 curiously recurring bugs. That's that's one of my favorite tech talks of all time. There's one that's like the strange case of stood string at Facebook. And then Tour of C++ is good. I like that one. I haven't read an incredible amount of books. Let's see. Yeah. I think mostly YouTube. Mostly YouTube is how I've done things. Yeah, what's up, Aditya? Okay, damn, this is... Is the OS platform independent? No, the OS is very platform dependent. It is extra work to make the OS platform independent, and so I'm just not doing that. I'm doing it really, really boring and just doing it very x86 right now. I see. Okay, so this is already a problem. So I had this idea where it could be kind of nice to make the buffers an internal struct, but then the problem is that anywhere you might need it, you need to pass a template argument. So that's kind of annoying. I think I'll backtrack that decision. We're just gonna go with this for now, which is a bit simpler. So we're just gonna have our scheduler buffers living over here. The scheduler gets a pointer to the buffers, and then now we just need to find all the places that use m task stacks. And replace them with m buffers.m task stacks. Okay. Hello. Okay, but then I screwed this up. So now that's the idea. So now all these things don't directly use mtask stacks, they go through the m buffers. And this is going to shrink the size of the scheduler struct significantly. What's up? What's up, Huanzhang? Nice to see you. And so now we're just always indirecting through the buffers for the big buffers. Currently, the only buffers really are the task stacks, but you could imagine there might be more very large buffers, and this is where they would go. So yeah, so let's make sure, let's go for a quick 20 seconds. Be right back. Feel free to join me for a stretch. Okay. So now what we need to do is and this is maybe a little bit interesting from a lifetime perspective. So now actually let me think, even, yeah, technically, actually this might not be necessary. We could maybe just do it all in here. Okay, so kernel's gonna take the buffers thing now, and and this needs to now take mBuffers.sketchway buffers. The interesting thing is that there's currently no protection controls on the buffers, and so theoretically other things in the kernel could access the scheduler buffers, which is maybe not as bulletproof as we want. We could even imagine something like a getter, and then this might take a badge. Actually, no. I don't know if that would really work. Well, I mean, maybe actually, yes. Take a badge for the kernel. And what this would let us do is something like this. Obviously, I want to return by reference. And with this badge, why not x64? It actually is x64. It's x86-64. Yes. This is just like old. This naming is just old. The badge thing just is this pattern I took from Serenity OS. So now the cool part is only the kernel can really call this method. Other random things, if they have a kernel buffers, they cannot access the scheduler buffers. This might be over engineered. But yeah. So now we're sort of just passing this up the chain. So now the question is, where do the kernel buffers come from? And that brings us all the way into K main. So now someone's going to need to construct, no, actually the G kernel, basically. So sort of looks like this. And technically, yes, we're doing some kind of strange things with global objects, but they are in the same translation unit, and then also kernel buffers doesn't really have a constructor, so I think this could be legit. This is a bit of a mess. Means large pre-allocated buffers that shouldn't be allocated inline in the kernel itself. Right. Oh, what's up, Eternal Divine Fox in the Twitch chat? Nice to see you. I'm gonna take this opportunity to update the text up top. Okay. Yeah, this might be totally over-engineered. Maybe I could delete all this stuff, but whatever. I'm just having fun. Okay, so yeah. So the idea is that basically, yeah, any subsystem of the kernel that needs to have large pre-allocated buffers is going to create its own buffers struct like this, and then have an instance in here. And then the kernel is going to pass a pointer to the buffers to that subsystem. That's sort of the idea. And that's actually sort of it. That is, it turns out we don't need this file anymore. So it turns out this was sort of it. Yeah. We haven't really run it yet, but let's just do that. So does the kernel still run is the real question. And it does. So just to reiterate, this is how things used to look. Big kernel object and like a lot of memory consumed directly in the kernel object. Also, a lot of memory wasted for struct padding. And this is bad. So here's what it looks like now. We no longer have the big stacks directly in the kernel. They're allocated separately in the kernel buffers. And the scheduler is now way smaller and just stores a pointer to the buffers. Sounds legit to me. What's up, Ruzu? What am I looking at? Very impressive. Thank you. Thank you. Just my little hobby operating system, which I'm working on very slowly over the course of literally years. Crazy to think. So here is the commit. The idea, yeah, maybe I'm gonna delete that for now. I think the idea is that really subsystems of the kernel should not actually ever know about the kernel buffer's type. They should really only take pointers to their particular member. So, okay, I'm gonna change it up. I'm just gonna say could use a badge if we cared about access control. Okay, nice. Okay. Making my own OS is my dream. Keep going, thank you. Yeah, same, mine too. And not really there yet, but we're getting there. So yeah. So extract, call it scheduler, extract stacks. I mean, we can even go a little bit more granular. Maybe we could even do a commit that actually doesn't do this stuff. Yeah, it doesn't. Yeah, so this, we could even break up our commit history very granularly. So we have one commit that sort of introduces an empty idea of a kernel buffers, and the kernel will just take a reference to it, but it won't use it yet. And we'll just have this empty thing over here. add concept of kernel buffers. And then over here, we'll actually start to use it. So now we'll fill in this thing, populate this thing, and do this. And so that is the ultimate awesome Git history for this. Extract stacks to scheduler buffers. Yeah, look at that. So pretend you're code reviewing my code. You're like, okay, interesting. Introduces the concept of kernel buffers, passes in, stores a pointer. And okay, now we're in scheduler. We're adding the scheduler buffers over here, fixing up the different call sites, removing task stacks. All right. Word. So that was actually a lot easier than I thought. And now we can actually I want to debug very quickly why I'm not getting my bin utils in my path. And it's because let's just RC exporting a bunch of these things will probably need this. And there we go. So now I got some tools available to me. And then now we can take a look at the G kernel thing. It's our new G kernel. And hopefully we can see that it is a lot smaller than before. Yeah, check this out. So this was from before and after. This was before our G kernel was 94 kilobytes. Mind you, this is a struct. A struct was 94 kilobytes. Yep. And these days it is still 24 kilobytes. So what's up, NSG? Nice to see you. What's up, Zek? What qualification do you have? So NSG, I'm just doing a small task right now. Small task is not storing large buffers directly inline in kernel objects, but rather having a separate object for really big buffers, and the kernel can get a lot smaller and then just store a pointer into these things. So I was wasting like a couple thousand so something like a heap. No, not a heap. remember, I'm still trying to do this weird thing where there's no dynamic memory allocation. So I guess, I mean, it's like a heap, but everything is pre-allocated. I guess is like a way to think about it, which sort of contradicts the entire idea of a heap. So I don't really think I would call it a heap. It's just an area of memory for big buffers that are pre-allocated, rather than storing them directly inside kernel objects and blowing up the size of kernel objects, and also wasting thousands of bytes of struct padding. I think the diff makes it a bit easier to understand. Like formerly I was just straight up declaring an array of task stacks inside my kernel object, right? That's 32K currently, and that's small. Like, we're gonna make that a lot bigger, and so I don't want to declare this massive array directly in my struct. And so now it's it's separately allocated, and then the scheduler gets a pointer to the kernel buffers, which is a bit elsewhere. And the idea is that's supposed to reduce the size of the G kernel. Although 24K is still a little bit, it's like a heap, but it's like a weird heap. Don't allow, dang, what? Oh my gosh. What's going on? Okay. The G kernel is 24K. Use elvim, read elf in path. The kernel elf is in build. Yeah. So like a heap, but the sizes are fixed beforehand. Kind of. It's a very weird heap. It's like, I mean, sort of the idea of a heap is that the allocations are like dynamic and stuff. But that's like, I mean, this is just my heap. It's like this struct that contains a struct that has an array with a fixed length. And so it's, yeah, it's really just a blob of data that is decoupled storage-wise from the actual kernel struct. So Juan Zhang saying, said array, I guess you have C++ 11. I'm using C++ 23, actually. Oh, dang, okay. Wait, I'm in the wrong directory. How do I resume? Dang. Okay. Interesting that it's still 24K large. From a quick check, why would that be? None of these things are too big. The interrupt hub, IDT is not really that big, right? IDT is an array. It's a couple of these arrays, so maybe that's some memory, but that frame allocator also takes some memory. This is almost nothing. This is almost nothing. It's just a few pointers. So, and the scheduler now should be way, way, way smaller than it was. Now, yeah, there's still, this would be part of the reason there. I'm still, the idle task stack is over here still. So that's a problem. So, but that's that is 8K. So yeah. source and setup.sh for read elf. How much of the C++ standard library have you been able to use? There's a bunch of it that relies on the underlying OS. Yeah, I'm using the subset of it that doesn't have dependencies. So I'm not using any of the stuff that actually depends on OS support. I'm only using types that have no dependencies at the moment. So I'm just having it diagnose. So there's 24K right now. We know that 8K is consumed by the idle task stack, which shouldn't be there. And so that still leaves like 16K. Of stuff. And it's probably between bitmap allocator and the interrupt hub, maybe. It's doing some reading of my kernel while that's going. Okay. Oh, the task list. Oh, that is interesting also. Task list. I mean, yeah. All right. So yeah, so let's just keep it. Let's just clean that stuff up. So this this thing should be here, right? We have the task stacks and then the idle task stack. So I just need to find mbuffers dot. Is it referenced anywhere else? I don't think so. So that's good. So we're gonna move this out. It still work good. Monkey D Luffy doing coding. Exactly. Yes, that's the look. All right. Let's figure out what's next. Yeah, I mean, about the... So the task list is actually surprisingly large. It is the ETL list, but a task is not big though. So that's not really, doesn't really fit into the idea of the buffers. A task is a pretty small struct. And so even though we might have a lot of them that get stored inline, that is okay. So let me fix this up. So this commit looks like this now. We're moving these two things. Okay, cool. Okay. So yeah, that means we are kind of at a transition point. This whole epic journey that lasted like the last couple weeks is somewhat concluded. I want to try one more experiment. I'm gonna what would happen if we just start increasing this number? I mean, all it's doing is increasing the number okay. So now let's say we have 8. Any better way to do this? Maybe we should use a loop instead. Let's just, yeah, let's just 8. Right, so we're gonna make 8 tasks, and we have 8 slots available. So seems to work. So just sort of stress testing. I mean, it's the lightest stress test ever, but you know, it'd be kind of cool if we could get, yeah, we want it to reach a bit more respectable numbers than like 8 than 4, for example. So now we have 16 tasks running. So I don't know, at least that's a good sign. Yeah. That's cool. Yeah. So but yeah, really the question is what is next? And a bunch of different ideas for this. Integration test, I mean, it's sort of time to look at the roadmap actually. One thing I would like to quickly test before we move too far forward is right, it's 2-guard page. This currently only tests writing to the first one, but okay, that's kind of annoying. But it would, you know, it would be cool. Okay, task -1. Cool to write, you know, just to verify things at a bit more of a slightly more reasonable level. Let's also write to the last guard page and just observe the page fault. Page fault. Okay, good. I mean, it's sort of hard to see how we could possibly mess that up, but because the loop is just like looping over all the task stacks and unmapping the guard page, but you never know. You never know. So that is just a tiny experiment. I mean, just off the top of my head, I'm just gonna brainstorm about what we could do next. One general direction is the task API, and so tasks can yield, they can exit, but there's other operations. There's like joining, waiting on another task, for example. All right, feel free to join me for a 20-second break. Ooh. What's up, VA80? Yikes, I'm late. I was watching F1. Also bought a Mac from my uni. Man, so we're both in the same house now. For sure, nice. Mac World. That's cool, yeah. All right. Join wait. I mean, there's this whole journey that I want to do of like working on all these sort of like scheduling primitives. Like, I mean, ideally we want to have like a mutex sort of thing. Some sort of condition variable-esque. What the esque thing would be cool. Hope Core. We got some F1 fans in the chat. You guys will need to give me an intro to F1. I don't know anything about F1. Straight up. I know as cars, they go fast. Y'all got to put me on. What are your favorite F1 drivers? No idea. Yeah. So what we're doing over here, we were doing task exit, right? Final task, all this stuff is complete. Idle thread, that's done. Task stacks don't run at the phys map, that's done now. So basically, yeah, this is a roadmap going back to March. Finally, I mean, this is the big one. Task stacks don't run out of the phys map. Phys smart pointer. Rethink the per CPU data area or not. Honestly, we haven't really gotten to that yet, so it's over here. Yeah, we made a lot of progress. All this stuff is yeah. The roadmap over here. I had some ideas. So turns out we're not really at the level of viewing pointers yet. Register state on the stack. Are we doing that? I think I actually did implement this, but it's not on this branch. So currently, no, the register state is stored in the task, but it's here, register state on the stack. So that technically is done too. Let me check. Mutexes are super nice to have, by the way. Make sure to have them at the earliest to avoid wasting CPU time waiting on spin locks. Yeah, I'm not trying to be a sucker waiting on a spin lock. I would never be caught wasting CPU time. Have some sort of ref counting on pages. Yeah, this would simplify shared mapping so you would avoid situations where one process has it mapped. Yo, Ismail, what is up? What's up? Adapt stress, just use AI. Bold suggestion in the chat. Word. Nice to see you, Ismail. Yeah, I mean, these are very valid. Very valid. because NSG has some good ideas usually, so we'll make sure to capture those. So here's what my plan sort of looked like a little bit. So we were just doing all this basic scheduler stuff, basic. This is even sort of obsolete, I think. I should say on the stack, sort of done. Yeah, the stack guard, proper virtual stack memory, that's officially done basically at this point. So yeah, my sort of plan was to get more into preemptive multitasking at this point. I feel like there's some primitives I'm definitely missing. And then it would be cool to do some drivers. So, yep. Hi, is your kernel POSIX? Sub black hole? No, not POSIX. NSG, no SMP yet. SMP is so far away. Dude, I don't even have a working single core kernel. Honestly, that's such a huge flex if you have SMP, as far as I'm concerned. Yeah, NSG flexing with his SMP Windows clone. Okay. Yo, digitalize, what is up, my guy? We got a, look at this chat, we got a stacked, chat is stacked as hell. Nice. Integration test infrastructure. I mean, once you get to preemptive multitasking, it would be worth implementing SMP at the same time to avoid headaches later on. Interesting. Interesting. So you sort of mean like, once you do preemptive multitasking, that's when you need to start caring about threads racing each other and interleaving. So you need to start introducing thread safety, and you also need that for SMP anyway. So you're sort of saying that you just gotta just sort of do both at the same time, sort of thing. Yeah, bring the cores and then the scheduling those. Yeah, I see what you mean. I definitely see what you mean. I think my approach is, I'm going kind of conservative with it. Like, I think I'll stay single core for a bit longer while I work on these sort of primitives. So the thing is, yeah, like, I would love to do this stuff. Realistically speaking, it doesn't make sense to add a spin lock if I don't have preemption. So I could choose to work on that, but I feel like there's still other stuff in cooperative world that I want to nail down before, and that is yeah, that's all this stuff with like waiting on another task, right? Join wait. So yeah, it would be cool to do that. Honestly, this is a boring topic, but I want to spend a little bit of time on this integration test thing. And this might be where I start to lean on AI a little bit to help me do this. So signaling primitives, I guess, like, well, like, yeah, like, yeah, waiting and signaling. Waiting and signaling, yeah. Stuff like that. Um, yeah, I think actually what gives me pause, I'm a little bit unsure about actually how to proceed. This is kind of a boring topic, honestly. Yeah, I think I probably won't do this right now. I think I'll probably think about it a little bit, maybe do another stream. Let's just focus a bit more on this stuff. So let's say we had a task that wanted to wait on another task. Something like that. Ismail, I think not quite yet. I think mutexes will sort of build on some more underlying stuff, I guess. Yeah. Okay. Like, what would it be cool for a task to be able to do? Be cool? Yeah, some sort of sleep primitive. Yeah. Yeah, we got nothing like that, and it would be cool to add one. So let's just like sketch a bit about how that would work. So sleep test. So we have a task, and I think I'm like genuinely a little bit puzzled at what I actually want to do. So a task should sleep on another task. Yeah, how would that work? So just to sketch out some pseudo code. Wow, what the hell? I mean, even a sleep primitive would be interesting. Just straight up sleeping a task for some amount of time, which is even more basic than this stuff. Sleeping, which requires, so to actually do that would require a bit of timer, some kind of timer integration, maybe. Let's something similar, not sleep, something similar to wait PID. I mean, yeah, like sleep and waiting are different things, but at some level, it's the same thing. I'm just like, okay, this thread goes to sleep and then wakes up at a later time, and then when it wakes up is just a different condition. It's like on the sleep side, it's when some kind of timer thing is ready, and then for the wait PID sort of thing, it's like when some event happens. Okay, I'm just gonna pseudo code it out a little bit. Like the typical way I would almost think this, the way this works in user space, it's like you have like a condition variable, and then one thread can be like, well, you need to have some state. It's like, you dot wait, right? Until something is true. It's usually in a loop. Yeah, I feel like Let me just see. Let's just sort of code it like really raw. Like, let's just say we have something super simple. We have like a bool is ready. Oh yeah, but the thing is, this requires a mutex, typically with a condition variable, which I also don't have. So, but yeah. And then the basic idea, it's sort of like while not kernel is ready, something like this. You do this on this side, and then some other task is like block mutex is ready equals true. Kernel.cv.notify. So use a spin lock. Oh wait, some sort of channel to sleep on. I have no idea how to even implement sleep in user space without busy waiting. Let's just call sleep. So this is sort of the idea, but I think I want something even more basic than this. Like, I think I'm sort of confusing this too much. I think really a good baby step would be, yeah, some kind of wait PID. Yeah, like sort of like what NSG was saying. I'm like, this is jumping a little bit too far ahead. I'm getting a bit confused. What I want to do is just be like, in a task, right, I want to just create a task. It's going to do some random work, and then the idea is that this thing should wait on that task. And the question is, yeah, I'm in need of serious help from the chat today. I think you could have a thread state variable and set it to waiting when it's waiting on something true. Your right user is ready as a signal. Yeah, maybe let me clarify my thinking. So I think there's some basic stepping stones, just to like zooming out to like 10,000 feet again. Like, the idea is we want to build out a robust task API of APIs that a task can call to do different. It's really like a scheduler, task scheduler API. And so it's a robust set of APIs that a task has to call to do different kinds of scheduler related operations. And the two like ultra basic ones that I have right now are yield and exit. So a task can yield, and like strictly speaking, create task is also a task API. And so the question is, what are some other like cool APIs we could have? We could have sleep. Yeah, we could have sleep. And so it's sleep for, I don't know, like 100 seconds or like even 100 ticks or something like this. But the question is like, I mean, we could use the timestamp counter actually. We could have a thread whose job it is simply just to be checking all the time if any things can be woken up here. But that's the key infrastructure we need. Just this infrastructure around like waking up. and implement sleep and stuff based on the state of the task object. Yes, 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 yes. State. Yeah, I think we'll definitely have a bit of thread state stuff. I mean, we already actually do. We already do sort of have this. It's not really particularly used. We just have runnable running, and the not runnable is interesting. I actually don't know if that's like really, that's only used, it's constructed into a non-runnable state, which is like kind of interesting. That actually isn't really used. I think all the people that construct the task into a runnable state. But anyway, we do have this area we can use to add some more states, so that probably will be relevant. Yeah. So Apex kernel, what is the name of the OS? Do I have a chat command about this? I forgot. Because I guess I don't. Yeah, the short answer is there is no name, because there's more important things to work on, like figuring out how to wait on tasks, than choosing a name. Yeah. Okay, so okay, so I'm just gonna make a simple call, and I'm really tempted to use AI to like help me get some direction here, but I'm sort of gonna not do that, and unless I like really get stuck. And what we're gonna do, we're just gonna try to do, and this is sort of again on the edge of my ability. I just want to find some way to do this. We're gonna create a task, and then somehow we're going to wait on that task, and then continue execution after the task exits. That is just a very, very simple thing to try to do. Yeah, all right, be right back. Okay. ETA when. Yes. So let's just wait. Something like this. Wait for task to exit. And we need to pass in something. And the interesting thing here is that create task returns no information about the task that was created. All it returns is a success or failure. So that's going to be kind of hard, because ideally we want some kind of something, some kind of handle that we can get after we create a task, and we can wait. So basically a PID is sort of like in user space, like sort of the idea. And maybe the PID is also what we want, but the thing is we're in the kernel, so we could even, I mean, we can use like kernel objects and stuff, and so like we could, like this thing could directly yeah, I have to warn you that this is on the edge of my knowledge, and I'm learning as much as, like, I'm just straight up learning in the moment right now, but we, instead of returning a bool, we could return a pointer to a task. And this is basically the task that was created. Update function declaration. So now it's like p task, third task, and something like, I don't know, something approximately along these lines. And then we can have no, yield. Where are my APIs? So task wait for exit, and again this AI I like this name a bit better. That was a good name. Task wait for exit and task to wait for. And then the idea is basically inside here we want to go to sleep, and then somehow in the task exit, here is where we can sort of hook. We can add some hook and wake up any waiting threads, right? So this is the reason why I chose this as the single easiest baby step for implementing any kind of sleeping and waiting on another task, is because we already have this like exit point to hook into at the end of the task's life, and that would be a very natural opportunity to like use that and then wake up other things, as opposed to like a timer, which introduces this idea of like needing to keep track of ticks or something like that, and then having this like entity who is responsible for waking things up. I don't have a timer tick currently, so I'm feeling a bit better about this being a good baby step. We got a suggestion from Apex Kernel Coding. No one should just try to integrate AI in this OS to boost user experience. Yeah, maybe we should do that. We'll just add like a chat bot somehow straight up into the serial console or something like that. Yeah. Okay, the big question I need to think through right now is, what is the state? So, and honestly, this is probably not really like a hard question, but it's just sort of like, what is the state we need to keep track of? So we're gonna have two tasks, and a task can have, maybe multiple tasks are waiting on another task to complete. So some notion of like, if a task might have, I think this is called a wait queue. And honestly, an NSG would probably know best, but like a task can have maybe like a wait queue to other, which are pointers to other tasks to wake up, something along those lines. So just to like, so let's imagine this is true. Let's imagine every task, in addition to like all of its wow, task HTTP. So in addition to this state, it's also going to store a container of other of tasks that are waiting on it. So some container list etc queue even of tasks waiting on it. And let's just say, I don't know, is it an ETL list or doesn't really matter? Let's call it the wait queue or something weird like this. And my and obviously we need a size here, so I'm just gonna put an 8. So at a maximum, and that's the sort of the thing about static memory allocation is at some points we just need to choose some random numbers, which is definitely a downside of the approach, but there I guess are other upsides. And so a maximum of 8 tasks can wait on another task at a given time. Do it. All right, let's do it the other way around to keep it simple. Add the task or object to wait onto the calling task. Interesting. So NSG, you are saying that waited on. So my idea was this, and you're saying actually do it differently. Saying do it in the other direction. So maybe just to even keep it simple. Well, I mean, it's useful to have a couple of these, I guess. So this task then keeps references to all the things that it is waiting on. Let's see. So then let's imagine, yeah, this way, instead of managing the tasks waiting on that object or task, the waiting task checks if the object or task signaled. So managing object or task, the waiting task checks if the object or task signal. So you're saying, right, okay, so you're saying something like this. It's like, the waiting task checks if this thing signaled or not. And like the waiting task like goes through these things and can like check if this thing signaled or not. Let me think about that. The main thing I'm a little bit unsure of right now is, so on the exit of this task, we're waiting on this guy to finish. We want, I want to go through and find all the tasks that are waiting on this task and then mark them to be in a runnable state, right? And so that was the idea, that was the intuition behind this idea, where it's like, okay, I got the task, I got all these pointers to these other things, and I can just go through here and then tweak these tasks to be in a runnable state. What if a waiting task dies? Interesting. How can a waiting task die? I'm gonna save all these chat messages because they're very valuable, and maybe I can read them all later. The way I'm doing it would involve going over each task and waking those up, mainly which can have issues. Some other task terminates it. Yeah. That's true. I mean, yeah, that is true. So some other task. I guess I haven't thought much about like killing or termination, but yeah, surely that is something on the roadmap, or that makes sense. So yeah, then you're saying, okay, this thing gets like killed randomly, then this thing just still has this pointer over here. Yeah. Also, what's up King Too Tall? All right, let me deeply understand this wisdom from NSG. So I think my question then, in this case, let's say it's like this. Let's say we have these two tasks. This task is waiting on these two tasks. This task is also waiting on this task. You're saying store calling tasks, wait, the managing the tasks. This is the part I'm wondering about. The waiting task checks if the object or task signaled. This part I don't really get though. The waiting task checks. So you're saying this, so the waiting task is going to be like checking if this thing signaled or not. But this task doesn't have any code execution. It goes to sleep until someone else wakes it up, right? So then my question is then who is, yeah, how does this checking happen? So maybe I'm being like super slow. I'll reschedule when the scheduler gets the next task and sees if it's waiting on something and then checks it over there. Okay, so you're saying on a reschedule and checks and sees if it's waiting on something and then checks it over there. So it's sort of, okay. So the way it works is like this thing is waiting, it goes to sleep, but this thing has this whole collection of pointers to other things it could be waiting on. And then at some other, like externally to the code execution of like either of these things, on reschedule events, we like go through and update things. And I'll make a red sticky to note this question about like, what if task waiting task dies? I think. Okay. I am very grateful to have some OS dev experts in the chat. So I'm down. I'm down to clown. I'm down to try stuff out. So that's kind of the whole point of this. Let's try it out. So but first I'll just get into this is all sort of junk. All right. So this is so instead of storing containers of things that are waiting on it, we're going to store. It's basically, I mean, it's still a container, but it's the opposite. It's like waiting on queue. Something like this. No. Actually, no. Tasks we are waiting on. Okay, so let's just try it out and see what happens. So, dang, did I just get a gift in the chat? I got some jewels from King $2. Oh my gosh. I saw something pop up here. Briefly, King $2. Thank you very much for the gold coin and the star. Got a big sponsor for our a happy poop for 10 jewels. Sick. Okay, appreciate it. Sponsoring this waiting work. Okay, so all right, let's think about this like this. So we got the waiting on queue, right? And what we're gonna do is in this API, we are going to, I'm going to snooze the inline suggestion so I can, in task dot waiting on queue dot replace back and interesting p task to wait for. So enter. There we go. And what's the problem? Oh, oops. Okay. So we need to set current task schedule state. So now we need, that's the not runnable. I'm just gonna add waiting as an explicit. This not runnable thing is like kind of weird. It's not really used. This isn't used just for init, so that's something to think about later, but let's go for the waiting. Right, so we're going to set scheduler state to waiting. We're going to emplace this thing, and then we're gonna yield, right? And my question is, what about interrupts and preemption? In general, like yielding definitely disables interrupts or disables preemption. Task exit also disables interrupts. Currently, push the waiting task first, then setting the state. Yeah, so that's exactly what I'm thinking. And so you're so in the if well actually BTW preemptively. So you're saying if in case preemption happens here, but I sort of don't think preemption should even be enabled as soon as we enter this function. Like my general philosophy around the scheduler is that when a task enters any kind of scheduler API, preemption just gets disabled. Like that was sort of a decision we made a bit earlier with the yield stuff also. So, but the thing is then task yield also just does this immediately. So maybe it's okay to do this twice, but yeah, I'm thinking we need this. And NSG, I'm curious if you disagree or not or whatever, but like I actually don't quite understand the reasoning why it would really matter the ordering. So you're saying like preemptively it'd be more appropriate to do it this way because if you get interrupted in something like this, I see what you're saying. You're saying let's say that a deschedule, like a schedule happens in the middle of this. You want to avoid a schedule where like you set the state and then don't yield and then the state is out of whack. I think that's my understanding, right? So you're saying it's kind of dangerous to like set the state first in case a preemption happens right here, which I actually do understand. And then so you're saying this way is like maybe a bit safer, but I actually don't. But then what if a preemption happens here? It's still the same problem because we set this stuff and then we get preempted. So this is my reasoning for why I'm pretty confident we need this CLI. So here, so yeah. Sub IO harsh? No, I'm using Mac OS. Yeah, okay. So I'm gonna go with this. And so actually I think, I mean, in this case, it doesn't really matter, but sure, as a general policy, setting the scheduler state as close as possible. The thing is, I have some rework to do, I think, because yeah, I have some rework to do because the scheduler makes so far the scheduler is kind of primitive and makes some kind of bad assumptions, and it hard codes this thing where it's like we always set the state to runnable if we go into a yield, and that's just wrong. That was like that's like a holdover from our like really simple setup where we just have like runnable and not runnable states. And so there's like something very fundamentally kind of flawed with my implementation. And so I need to figure out how to fix that. And so the idea is that we don't want to just hard code this. The caller of the yield is the one that's like who's really deciding what the state of the task should be. So I'm just going to take a screenshot of what's kind of bad here. is to assume the task wants to be put into a runnable state, right? What's up, Ankit Gala, joining for the first time. Can you summarize on what you've been building, how to navigate through your channel? Yeah, it's just my own OS, doing it for 2 years now. First year was doing this MIT OS course. Second year has been actually building my own OS in C++. Yep, okay. So let me think. So before I got another gold coin from King Too Tall. Thank you. So even before we continue with this stuff, what I want to do is actually refactor this sched state management. So really it's all about, we're now moving the responsibility of setting the state to the caller. So the question is really, who are the callers? And what's the deal with the yield impl anyway? Yield impl, is like this internal function of the scheduler. Yeah, the way things work right now is like we have task yield, which is it's like sort of like a outer API, and then yield impulse is used internally, and a task can call into task yield, which does the low level switch and jumps into assembly and whatever. And the whole idea is we want to return back out of assembly and into C++, and that's the main purpose of yield impl. So that's just the architecture. Whew. Yes. And so then the problem is that the state was hard coded here basically. And so inside yield impl, we were hard coding runnable, and that is not really good. We want to actually kind of bubble this up, and I'm even wondering if it even goes up here. Does the client pass the state? It sort of seems like it might be that way. So task yield. Who are the callers of task yield? We pretty much just have these callers. So what? I might add an argument. Task. New state. So now we're just going to go over here. We're going to make this, and maybe if any of the experts have some advice, we can talk about it, but all right, I'll be back in 20 seconds. Oh man. All right. Again, quick shout out to anybody in Europe right now. It is sweaty. Sweaty. Okay. So any of the experts in the chat can correct me if I'm messing up big time, but maybe so that's sort of how it looks now. So now clients need to actually pass the intended state of this. Brings us to here, which is now where we can say waiting. Heat waves have been crazy. I don't know if it's been the case in Asia too. Yeah, who knows? So yeah, now we've like decoupled, or we've now like stopped hard coding this. Now we take the task state new state block interrupts. Yeah, I'm still kind of deciding how I want to reference the current task, but whether it's with this thing or whether with this thing. Yeah, maybe we'll go with the method. I don't know. We set the state, and then now we drop into the assembly, which is not even important, not important for this thing. We enter in here, and then this thing goes away. We don't need to do this anymore. So we've corrected the problem and moved the responsibility for deciding exactly what this should be, right? What should this new state be? That's not something that yield impulse should be deciding. It's like something a client should be deciding, I think. So of course, now here's the point where I want to make sure the kernel still kind of works. And so but my kernel is in a super broken state because I was sketching out the weird all this weird stuff, which you don't need. And CP. Okay. Yeah, I don't need this anymore. This is also sort of whip. I just want to make sure I didn't break things. This is the part where it would be so nice just to have some basic unit tests helper. But it looks like the kernel is working, but also, like, honestly, I don't have the tests, so I don't really know. I mean, it seems like it is working. At least it's not crashing. So yeah, I do want to get some tests, some integration tests going, so I can check that things work. But that's the idea behind this. And so what is this? This was some stuff. Oh dang, this is too much. All right, let's figure out what I want to commit. So That's not for now. Okay. Okay, so now I want to also go here. Okay, and this, nope. Not yet. Okay, so here are the stage changes. We're just tweaking all these call sites to pass runnable. And we are taking a new argument here and tweaking the call site, deleting this thing, and using it right here. And I'll just add const. So scheduler, extract, move risk, or maybe set yielding task state in caller. Right. This thing, this tiny little hunk should actually be in this commit. Okay, so now we have our awesome commit that refactors that thing. Check the chat real quick. No new messages, okay. Starting to think now writing a kernel is actually achievable. Oh, don't think too soon. We yeah, got a long ways to go, but yeah, very little subset of features and no crazy drivers. Well, no drivers at all whatsoever, and basically no features. Like basically, I mean, if we wanted to make a computer hot, we could definitely do that with my OS right now. We could absolutely like heat up a CPU. Just get some tasks going that like start computing some math. So yeah, definitely can do that if we wanted to. Okay, so now let's get back to what we were doing originally. So now wait for task exit. So now that we've done this refact, we can actually pass in this OS can cook an egg. Can pass in waiting as the state we want to set the task to. So the CPU if needed. All right. And naturally, you know, the thing with all these containers is they have a fixed size, and so we're just gonna assert what is it? Full. We're gonna assert that it's not full. And we don't really have a good way to error handle this, to be honest. If like straight up, what do we do if a task is trying to wait on another task, but it's already waiting on the maximum number of tasks it can wait on? What do we do? Do we fail? We could return maybe. I don't know. I don't really know if this would be useful. We could return an error, something weird like that. But the tricky thing is it's always a little bit tricky with these things because I guess now we need to make this thing return true after it returns execution, but that's like a little bit more fiddly than I want to do right now, so I'll just keep it with an assertion. Good. Right. Handling. Error. Would a client realistically do on failure? So yeah, so we're gonna revert this. Okay. So here's what we got so far. We're gonna bring this back. We got the sleep test. We're gonna create I'm just gonna create like a little like noop task. This the sleep. It's really like the wait test. The wait test is going to create the no-op task, the noop task. Make sure that successfully happened, and then we're gonna wait for exit. And we're going to panic. Succeeded and resumed execution. Panicking is the best way to see if something worked. Okay, so here's the idea. So we're going through task wait for exit. Let's really wait for other task exit. Task wait for other task exit. Just to be very verbose and almost maybe a bit unreadable. The reason task is at the front is to make it clear that it's part of the task API. Like task yield, task exit, task wait for other task to exit. So we can always change the naming later. So we're going to make sure it's not full. We're going to emplace back, going to make the current task go into a waiting state. And then we're going to yield, which is going to hit the scheduler. And so now, this is sort of the key part of what NSG was saying. So now the idea is that on reschedule, when the scheduler gets the next task and sees if it's waiting on something, and then checks it over there. So NSG is saying, okay, like, right, so this task goes straight up, just goes to sleep. It's not running at all. And this thing gets some execution time. Actually, I need to remember to kernel dot, yeah, scheduler task exit. That's mandatory. Tasks need to exit. And then this is going to trigger a reschedule. And I guess, where's this going to happen? So at some point in the scheduler, we just so we mark this thing as exited. And we enter the scheduler, and then we enter the policy. So here's where we could theoretically do something. And what we would want to do is I understood it right, the suggestion is to basically go through every task, check all of the the things it might be waiting on, see is this guy exited or not? And if it is exited, we then remove this thing from the container and well, actually actually, how is it possible for a task to be waiting on two tasks? I don't actually know if that's possible. How would you do that? It can definitely be in the other way around where I don't think so. I actually don't. I don't really think so. So let me think about it. In general, usually a task blocks specifically some. Well, if it can wait on a thread, for example, it can block on a mutex. Multiple things can be waiting on that mutex. And so from the mutex's perspective, it has like 5 things that are waiting on it. But from the thing that's waiting's perspective, it's waiting on one thing. So I actually don't really know why we're using a container. A task can wait on multiple tasks. Am I being slow with that one? I mean, yeah, like you can wait on multiple file descriptors, for example, but that's like a really Linuxy thing. Let me you can make it wait on just one or all. What NSG, what API are you talking about specifically? Am I not, because I'm thinking of PID straight up. Refresher, what is wait PID? So you're saying wait PID allows you to wait on multiple tasks. Until I see, suspends execution of the calling process until one of its children terminates. Interesting. So that's a little bit different because that's talking about processes. Wait for single, wait for multiple objects. I see, okay. So these are some APIs that I'm not intimately familiar with. Especially in the Windows NT world. Okay, so yeah. Okay, so it is theoretically possible that you might want to wait on multiple things. So in that case, so there's multiple cases here, I guess. It's like wait on single, wait on multiple. So if I understood it right, the idea is that we need to go through on every scheduler tick. We need to go through all of these things, check, see what waiters are there, and then update the state in case this thing exited. But then the question is, at what point do we up the state? So processes is not equal to tasks. Yeah, processes are not tasks. So it's a little bit, the terminology is a little bit confusing, but it's sort of like, from a user space point of view, you have threads. You have threads, and then like a group of threads is like a process. From the kernel's point of view, everything is just tasks. Like it's sort of like threads and tasks are sort of like one-to-one things. And there are reasons why a kernel doesn't call a thread just a thread on the kernel. But yeah, from the kernel's point of view, it's just like all these things that just need to run. And whether or not they share address spaces or whatever is like sort of irrelevant. It's just like the kernel is just like has a bunch of tasks. It's just trying to like schedule and run. So I think that is a slight difference with WaitPid, but it's a slight pedantic detail. This still does prove the general concept of like one thing like waiting on like multiple things to finish. I think NSG is actually talking about some kind of more specific Windows API, which I am not familiar with, but wait for a single, wait for multiple. I wonder, yeah, I actually don't know those APIs, but I wonder if it's more like epoll or like select or something on Linux. Wait for multiple. In which case, that's like actually kind of different. I think I actually want to take a moment to wait for multiple objects. Dang. The blocks until one or all specified kernel objects entered a single state. But this is also different because this is like about or maybe it's similar. I mean, it's even more general, I suppose. It is arbitrary waitable events, which can include threads. So I see. So I think I would consider this sort of like epoll or select. I sort of forget the difference between epoll and select. But okay, so point taking, yeah, like, yeah, there's like sockets, yeah, like there's like all sorts of different things you could potentially wait on, like file descriptors, you know, threads, all sorts of stuff. You can, with wait functions, you can pass in any sort of object, so you can wait on a thread along with an event, right? That's actually like pretty cool design. You might consider that pretty clean design actually, where it's like the idea of like an object's like waitability is sort of abstracted, and so different kinds of objects can just like implement being waitable. And I think the situation is not as clean on links. I mean, you do have file descriptors, and so to a certain extent, yes, you can just like wait on like arbitrary file descriptors that are backed by different kinds of things, so that is maybe kind of similar, but also like not everything is a file descriptor. Like a mutex is not a file descriptor. So I think that would be one example where it's like actually like the wait for multiple objects is like kind of goated, because then it's just like mutexes, threads, process, like whatever you want. If you can wait on it, you can wait on it, sort of thing. Anyway, let's just try to like, I just want to like sort of slightly get this working. And so my decision I need to make now is like, where do I actually put this code? Because the policy, really its goal, its main purpose was to choose a next task out of runnable tasks. And so like adding all this extra logic to like update the task's state is not really awesome. And I'm thinking it's just something that we run like right here. It's like, and it's just sort of like update waiting tasks. Check and update waiting tasks. Could even be like a normal function, but the idea, if I'm understanding this correctly, which is always a chance that I'm not, is like we need to go through here. We need to go through every task. Yeah. How do we want to do this? I'm just gonna sketch it out for auto task and tasks. For auto p okay, task dot waiting on queue, right? So what's the naming? We're gonna, for every single task, for every, maybe like waiting on, waited on task being waited on. But then here's the question, it's like, well, what's the condition? When do we actually set this thing to runnable or not? Like in the simplest case where you can only wait on one thing, this thing is just waiting on like one task at a time. It's simply just, if this thing is is exited, then this thing gets to be marked runnable. But now it's like, well, what's the deal if we're trying to wait on all of them? I think that needs to be a different API. Wait a sec. I think that needs to be a different API. Now I'm getting a little bit lost actually. So I'm just going to implement the simple case for now. So let's just say we want to wake up when any of these wakes up. And so if and also realistically this pointer, sort of interesting, this should never be null. I mean, wait on. So to use a reference wrapper, I'm gonna use a reference wrapper instead of this. Sched state equals exited. Then task So, right, so if there's like, runnable, and at some point, it's like a little bit weird. Like this is sort of doing it in every loop, which is not good, but it's like if yeah. What I want conceptually is like if we're in a if we have anything in the waiting queue, then we must so I'm just gonna do this in a bad way right now. Task.waiting queue dot empty. It's not empty to assert. So if the task, the queue is not empty, right? So the list is empty, right? So if it's not empty, we have things we're waiting on, then we should definitely be in a waiting state. That's just an assertion we want to do. And then now we're going to go through all these things for all of the waiting on, task being waited on. Waited on. We're going to mark ourselves as runnable. And then we're going to, we want to remove ourselves from the list, but we need to watch out for iterator invalidation actually in this case. I don't do this enough to really know actually. So we might actually have to use iterators a bit more manually actually. Let me think. So auto it equals yeah, while yeah, it's like while the iterator is not equal to the end. Okay, I'm just going to snooze 5 minutes. Okay. On it. Then like this, I think. It equals task that waiting on to dot remove it. And here's the part where holy crap, it iterates the list to find. Wow, no way, I can't. Oh, wow. ETL, come on. That is very unfortunate. Also, wow, it's super weird. So let me pull up the list. Or is it erase? So this is how I expect lists to operate. You pass it an iterator and it returns the thing. Yeah, not familiar with these not familiar with these C++ APIs. Do you expect a return on remove? Yes. That's what I was trying to figure out. Like usually the way it works is trying to remove something, and the remove API will return an iterator to like the new next, like the thing after the one that got removed. And I was just verifying with the standard linked list. And that's how it works. That's how you can see that right here with the erase. We get returned an iterator. Iterator following the last removed element. Yeah. And then so you can use that to implement your like loop that like removes things in a safe way, because one of the tricky things with C++ is you need to make sure to not invalidate your iterators, and inserting and yeah, removing from a container can invalidate iterators. At least like for things like vector. I think list actually is sort of different because it doesn't invalidate. Wait, references and iterators are invalidated. To other references and iterators are not invalidated. So that's the interesting thing though. Actually, yeah, like sorry, validate. So this is a little bit different because you don't need to worry about the same iterator invalidation problems, but yeah, what was happening is like ETL actually is like just different, and so this is yet again a situation where ETL is making it hard to, it's really hard to actually recommend ETL as much as I would really want, because it looks like such a cool library, but it modifiers. Okay, so I'm confusing. There's remove and then there's erase. Remove uses a value, which requires this like slow ass like iteration over the list. I want erase, and this is exactly what I want. So I take everything back. ETL is freaking awesome. I love ETL, best library ever. Yeah, right. So erase is what we want. Remove is more of like a helper utility in case you don't have an iterator and all you know is like the value of the thing. Like if you have like a container of like numbers and you want to remove the number 42 from the list, you can just pass in 42 and it'll like walk it and remove. And also notably, actually this is actually interesting because yeah, what am I'm like Oh, this is cool. Wait a sec. So basically, what I have done right now is I've basically manually re-implemented remove, and I didn't even realize it. But you can see that you can see you can see I did almost exactly the same pattern. The way you implement removing something from a linked list or whatever these containers with iterators is you get the begin, and you just like while the thing is not the end, you then have some condition on which you want to remove it, and then you do the removal. You call it erase. Otherwise, you increment the iterator, and I've actually accidentally re-implemented which is actually kind of cool because it yeah, maybe we can actually use some of this stuff. So yeah, let me see. We're trying to remove. It's really the remove if. We're trying to remove if. So the only hitch in the plan is this. So we could and this is actually sort of what I was hoping to really do the entire time with this ETL stuff is like really test out what a modern C++ auto, what is it? It's auto. Yeah, it's like this, right? Modern C++ OS would look like, and this is sort of how it sort of could look like, where we are using more higher level algorithms. It's like we want to remove all the things from this queue whose scheduler state is exited, and that's super close to this thing that I manually wrote, with the one hitch of like I wanted to update the task to be runnable in case any of them actually was removed, but unfortunately I don't actually get any feedback if something was removed or not, which is kind of unfortunate. Let me see. Let's go for the yeah, so this is what I want. I want to know the number of elements removed. All right, be right back. So at least that's sort of the idea. So we might have to patch this. And I think I think the AI will know exactly what it wants. So we're just gonna patch ETL to count the number of things that got erased. Const auto num removed, and then if num removed, basically if num removed, yeah, set. So that's basically exactly what I implemented before, right? We're setting this thing to runnable. And so the difference is, look at how much code this is versus this is. That's why vendoring is such a great thing. Yeah, totally. Yeah, it is. It is pretty nice to be able to patch things at will. Um, of course, it's even better if you don't need to patch it in the first place, but um, sometimes you just got to patch stuff. So we be patching, maybe for good measure. I'll just do this over. Yeah, should I do both of them? Nah, I'll just do. I'll do it later if I actually need it. So we're just gonna patch it, and then now that's sort of the idea. Okay, so here was my initial failed attempt, and it was a failure because I was using this for loop thing, which is that's like the foot gun. Like you do not want to erase from a list that you are iterating with the for. In general, I mean, it really depends on the iterator event invalidation, and maybe lists are actually okay to do this. I'm just gonna ask the AI. Is it okay to remove from a std list while deleting elements from it? I know in general, iterator invalidation would make you not want to do this, but maybe lists are different. Let's just ask the AI. Wait, what am I saying? Remove from a list while iterating it. Hopefully it knows what I meant. Okay, so it's saying for std list, erasing elements is generally safe in a way that is not, right? So that is like one exception. In general, you don't really want to be doing this for loop kind of iteration while deleting things, except apparently list is actually sort of okay to do that because when you insert or delete, it doesn't invalidate other iterators to other things. It just invalidates the single iterator. But wait a sec. Okay, but it's saying this is actually not okay. A range-based for loop. Okay, so actually, wait a second. So we must handle the return value of erase carefully. Yeah. Okay. So I will retract what I said. It's just important just to be careful in all cases, and don't use this handy for syntax and then start deleting things from the list. It's bad idea. So this is what it looks like. Check. Okay. Let's just take. So we're going to check and update waiting tasks. Go through all the tasks. We do our. There's a better way to do this, but I won't do it now because it's. Or maybe F it. I will. In general, it's like it's going to be something. Cert. So. Just so if. Okay, so if it's empty, that's okay. We just go through. But if it is not empty, then we want to make sure that this thing is waiting. All right, if it's empty, that's fine. It's not a requirement for it to be empty or not empty. It's just in case it is not empty, we want to assert that the task is also in a waiting state. It's an invariant. Yeah. But the music, I have been playing this like lo-fi playlist from YouTube for like 2 years now. I think it's called like the Blockbuster playlist or something like that. Blockbuster lo-fi playlist, something like that. Okay, so we're going kind of late today. I want to wrap it up soon, but I think this is a basic version to do this. So this sets the task to runnable if any of the waited on tasks exited. What about waiting for all tasks? That's sort of different semantics, and I wonder, yeah, it might even be a different kind of waiting state. We could add like waiting on one or waiting on all. Maybe that's how we would represent that. Different task state, because then we would be able to check that state here and appropriately like modify like the semantics and be like, okay, if it was waited, if it was simple waiting, if any was removed, then we set it runnable. But if it was waiting on all, then the num removed has to be equal to the previous size of the list. So without further ado, let's test this. And so the idea is that on rescheduling, we're just going to do this like check, and hopefully it's not too expensive. I mean, we have to iterate through every single task. So I think that would be my main critique of this suggestion from NSG. Like on every reschedule, you need to but on every reschedule, you need to check all tasks. There's probably ways to optimize this. Yeah, there's almost certainly. Yeah, I'm probably doing this in the worst way. Like probably the real kernel developer way to do this is you keep some kind of container only of the tasks that are waiting on something, maybe obviously, and then you just iterate through that container. And so that's actually an idea to do. Store these tasks in some separate list of everything waiting. Yeah, that's probably the idea. Yeah, we sweaty today. Okay, but for the moment, our kind of stupid, just like iterating check will do the job, I think. And let's just let it rip and then call it a day. So what we're gonna do is it's called the wait test, I think. We're just gonna run the wait test. And again, this is like pretty basic. The wait test is gonna run. It's gonna create a new task called the noop task. It's going to it's going to wait wait for other task to exit, right? we're gonna add this task into our container. But this is maybe kind of interesting also. I mean, NSG had this point where it's like, well, what if the task dies or whatever? Like what if a waiting task dies? And so it was like problematic. Like what if you have all these pointers over here and then this guy dies all of a sudden, you have this dangling pointer. But can we have the same situation over here though? We're waiting on and this guy just dies and we have this dangling pointer. So don't we sort of have the similar problem? So I don't know if he mentioned a solution for that. Okay, well we will see. NSG is more experienced than I am, so anyway, we're gonna wait for other tasks to exit, and we're gonna block basically, and then I will actually just add a print started and exiting. We're gonna see a print from the noob task, and then this thing should wake up again. And we panic. So let's just run it up. Moment of truth. Are we ready? All right, let's go. That work? Succeeded and resumed execution. Noob task 2 started and exiting. I think that totally worked. I think that totally worked. Yeah, just for fun, key debug thing. It's always fun to step through these things a little. Okay, I forgot my helpers. Wait, test. So we're gonna, right. We're in the wait test right now. So we just created the new task, and we're going to wait for other tasks to exit. So let's just step in here, disable interrupts, and queue this thing, set our state to waiting, go into task yield. And yeah, we're gonna step through the scheduler, the context switch assembly, and we're gonna pop out over here in yield impl, which is where we're gonna hit our check and wait, and we're gonna go through our tasks. There's not really that many tasks, so this should not be too bad. Task is kind of hard to print out. Honestly, it doesn't really matter, but wait, can we see something cool? Waiting on queue. Node pool. Having a bit of trouble reading this, but whatever. So we're going to call the remove if on this, remove if it's an exited state. And so this should be 0 because the noob task has not even run yet. And so nothing is going to be removed. And so none removed is 0. So we're not going to do anything. Now we're going to check. Yeah, it's like checking the other task. This is the noob task, I think, so it's not waiting on anything. So we're going to finish. We're going to select. I'm just going to p next task dot id task id 2. Yeah, I'm pretty sure it's the noob task. I could even give names. NSG, when FK, where are you at now? So we were just testing out the basic implementation of things, and it seems to work. This is, yeah, we're in the middle of stepping. Okay. Yeah. I kind of exited a bit too quickly, but let's try that one more time. Yeah. Let me get back to the right state. So B wait test, right? So we're gonna go here. Step step going to break scheduler yield impl, go here. So NSG, I want to show you this stuff too, though. So this is how I was doing it. I was not sure if it matches your expectation, and so um, on the reschedule, the first thing I do is we check and update waiting tasks and get them all into a runnable state if uh, necessary. And then later on, the normal scheduler policy just runs and just chooses a task. And so this is separate though. And I'm using all this cool C++ stuff to make it a little bit more compact. And so it's just go through every task and removing anything from the wait queue that is in an exited state. And then if anything has been removed, we mark the task to go into a runnable state now. And I feel like it looks pretty nice, pretty clean. Pretty clean. I actually don't need to capture anything here. So yeah, that's what it looks like. What I want to just see is us break scheduler check. So what I want to actually do, I'm going to break in a few points. I want to break on task exit. Task exit. So now we're going to break on task exit. So now the noop task has started and exited. And so now we're going to be in a great position to observe the logic that's going to check and switch the wait test task into a runnable state. And that's going to run pretty much right here. We're going to call it, yeah, straight up right now. So the task exit calls into yield impl. We're going to go into check here. And I wonder if I do this. I cannot do this. Also, M tasks. Can we? This is so hard to read. I am looking for any kind of size. Items allocated. Doesn't really matter, but let's just. So I don't really know what task we're in right now. It might be useful for debugging to have like a text name of task actually, but let's just see. So let's see. So this one actually had one removed. So this one is the waiting the wait test thing. And so that means we're going to go in here and set itself to be runnable. In the next iteration of the loop, I don't know. I think this is going to be the task that just exited actually. So it should not have anything. That's going to be 0. Now find a way to break your implementation. I'm sure, yeah, there are probably some pretty good ways to do it. Probably, yeah. Probably a bunch, yeah. So now the policy is going to choose a task, and it would be really cool to have a string ID for the name of the task. That would be so helpful. Maybe it's something to add a bit later. But anyway, we're just going to, it gets the task, we're going to switch into it. And how can I most easily destroy task? So we're doing the deferred cleanup, restore task. We're going to step all the way to the ret and moment of truth somewhat moment of truth. Hello. Okay, and then here we are returning from the wait for other tasks to exit thing. So we're returning from the last few instructions of this function. So now we're finally resuming out of here, and we're going to resume back to the panic and hit the panic. And so, yeah, dude, these effects are so cool. Yeah, um, so we did a baby step. We just got the actual most simple thing working for one thing to wait for another. But actually, while NSG, I don't know if you're still here, but I have a question for you. So you were saying it's problematic. Like, what if we store this pointer over here, and then this guy dies, right? Um, I was wondering if we could just have that similar situation over here where this guy's waiting and then randomly this thing dies. And now we have this dangling pointer over here. So my instinct to solve both of these problems, because it seems to me to be basically the same problem, is to have some kind of weak pointer thing, which is usually what you do in a case where you have a pointer to something, but that thing might like actually go away during the lifetime, so you want to be able to check. You usually keep a reference count for that. I see. So you're saying, for example, in this case, the task would be ref counted, and it would only be destroyed or something once there were nothing pointing to it. Yeah, reference counting, interesting. So I wonder if you could do that on this side also. I wonder if you could also just ref count this guy and be like, hmm. Well, wait a sec. Yeah. Hmm. Interesting. I guess either way, yeah, maybe need to think about it more, but word. Oh my gosh, apnobenzene. You're late, and literally I'm about to end the stream. It's been like 3 hours. Um, but then it's just easy to check if something did something, then informing the logic everywhere. Yeah. Yeah. I think I just need to develop more of an intuition around this kind of stuff. So my intuition was that it would be just sort of like nice to just sort of on the exit just go through this whole thing and wake everyone up. But it's also true that maybe this guy is waiting on multiple things and it doesn't want to be woken up yet. But that's also possible. Like we just go through here, we check, okay, is this guy in a waiting state or a wait on like everyone state? Maybe it is a bit more complicated. Maybe it is easier this way. Yeah. Basically, if you check in the scheduler function, the check function inside checks and wakes up the task accordingly. See you next week at 8 p.m. sharp. All right, let's listen to some wisdom from NSG and then we'll call it a day. Basically, that works too, Ben. It's easy to check if something did something, then informing the logic everywhere. Basically, if you check in the scheduler function, also hold up. I think We lost them. Did we lose the music? Basically, if you check in the scheduler function, check function inside checks and makes a task accordingly. If you have a waited on list, an exit function, or the list would also be responsible for waking. Right. So, okay. I think I see what you're saying, and so doing it this way to some extent allows for centralizing the logic to some extent or something like that. But over here, then like the exit function needs to have a bit of logic injected into it to do things. Then the mutex release also needs to like have to like do all this stuff, and then you end up scattering like every single place in the kernel that could possibly be a source of like waking something up. It needs to get a bit of code there. I think I see what you're saying. So you're saying that like it's sort of nice to not do that and just have it all be centralized in one place, if I understand correctly. You're copying the same function everywhere at that point. Yeah, interesting. Okay, well, it's something to reflect on for later. This was a really cool stream. I'm really appreciative of all the support today. Honestly, I was like a little bit intimidated by how to even start with all this waiting stuff, but this was pretty cool and definitely a nice little baby step. We swagged out and used the remove if with the ETL patch, which is pretty swag, and we swagged out and have this task wait for other tasks to exit new API, which is super shiny. All right, I think I gotta end the stream here, y'all, but it's been real. It's been fun. Have a great week. Stay cool if you're in Europe. Please subscribe to my channel if you're watching and digging the content, and I will see you in the next stream. Maybe next week. I'm not sure. I might have to dip out next week, but yeah. All right. Peace. Later, everyone. Bye.